Hello, welcome. Let's We are looking at section 5.2, the growth and decay section, and we're going to start with example 5. This is part 2 video. And on this, we can see that we have some half-lives given, and example 5 says, suppose that you took 10 grams of plutonium Pu-239 that was released in the Chernobyl nuclear accident. How long will it take for 10 grams to decay down to 1 gram? I also notice up here that they give us the half-life for plutonium. So we're going to make use of that little fact as well. All right, so at time 0, I have 10 grams. What I'm trying to figure out is at what time do I have 1 gram? How many years is that going to take to happen? And what I need, I know also the half-life. The half-life of Pu-239 is 24,100. So in other words, if I start with 2 grams, I'm down to 1 gram in e to the 24,100 K time. Because we know this is a growth decay model, Y equals PE, or CE if you'd rather, CE to the KT. So I plugged in those things that I know. Divide by 2 and I'm at 1/2 e to the 24,100 K. And then natural log both sides. I have the natural log of 1/2 equals 24,100 is my K. Let's solve for K. So I'm going to have natural log of 1/2 divided by 24,100. All right, now that we've got K, we can go and complete the rest of the problem. So it wants to know how long it's going to take to go from 10 grams down to 1 gram. So I know I started with 10. I want to finish with 1. E, I have my K value, natural log of 1/2 divided by 24,100 times the amount of time it took. Okay, now divide by 10 and we have 1/10, or let's just go 0.1. How about that? 0.1 equals e to the natural log of 1/2 divided by 24,100 t. So we will natural log both sides, and I'll have the natural log of 0.1 divided by the natural log of 1/2 divided by 24,100. But that division by will become a multiplication of 24,100, right? Dividing by a fraction is like multiplying by its reciprocal, and that gives me my time element. Time turns out to be 80,858.467 years. That plutonium isotope is going to be around for a long time. Number 6. This one has an example where you're given 2 quantities, and how do you work through on that? So let's do this example here. An experimental insect population increases at the laws of according to the law of exponential growth. So y equals some amount e to the kt. There were 250 insects at day 3. So I'm thinking of time and insects, kind of my ordered pair. So I'm going to have 3 and 250. Also, 400 flies at day 4. So 400 on day 4. 400 insects on time 4. Approximately how many insects were in the original population? Well, this would be what I would consider the original population, right? Okay, so how am I going to do this? I don't have a K value, so that's going to be my starting point, and as it is often. So I need to find K. And that's going to look like the equation y equals c e to the kt. And I'm going to use these ordered pairs. So if I start with 250, I finish with 400 insects. How much time did it take for that to happen? Some K value. 4 minus 3 would be the days that it took for that to happen. So in this case, 1 day. And then I'm going to divide by 400 divided by the 250 equals e to the k. We could reduce, we could reduce a little bit more. Let's do it. 8/5. So 8/5 equals e to the k. Natural log of 8/5 is our k value. Now that we got k, we can go solve the problem. So now we know k, as well as we have a starter amount that we can work with as well. So how many insects were there in the original population? Well, we know k was natural log of 8/5, and I have the 250 quantity, right? So I'm going to set this up y equals c e k t. I'm going to have my outcome be equal to the input e to the k natural log 8/5 times the time that expired, or 3 minus 0 time frame. So 3 days expired, because I'm using the ordered pair 0C. Okay, and let's see, what can we do to help solve this? Oh, well, basically, let me simplify over on the right. I have e times 3 natural log of 8/5. This is a number, isn't it? Let's just divide by it. That's all we have to do. The original population is 250 divided by e to the 3 natural log 8/5. Just be careful putting it in your calculator, but you should get a C value of 61 insects is what that population started at. Newton's law of cooling. You did Newton's law of cooling last year in pre-calc, and I think that you probably came up with a temperature final that, so some temperature according to time, with T being the surrounding temperature, and I let that be my S, the temp of the surrounding, let's do T sub S, I'm sorry. T sub S, surrounding temperature, plus T of the object minus the surrounding temperature. We're going to gather what that temperature difference is, e to the kt. So starting the temperature of the object, I'm going to call that T sub 0. A cooling constant specific to the object, that's my K. And time is little t. So knowing that, I could take this statement. Now let's read Newton's law of cooling and see how we get this differential equation. Newton's law of cooling states that the rate of change in temperature of an object is proportional, there's the K, to the difference between the object's temperature and the temperature of the surrounding medium. So the difference between this temperature of the surrounding medium, that's that inside piece that we're talking about, or this value right there. Okay, so it's the rate of change in the temperature of an object is proportional to the temperature differential. Alrighty, so knowing that, let's take and work this example number 7, and then we can call it good. Alrighty, switching back here to get a nice pen. A 250-degree meatball is removed from a simmering pan and set to cool on a plate in a 70-degree room. In 3 minutes, it's now 200 degrees Fahrenheit. How long before it falls below 140 degrees and into what we think of as the danger zone, where bacteria can begin to grow or thrive? So the TO, this is the object's temperature, and that was starting at 250 degrees, the initial temperature of the object. The surrounding temperature, that's my room temp. So that was a 70 degrees. In 3 minutes, the temperature final, or it kind of comes down to 200 degrees. From this information, we can gather what K is. So once again, starting out with K since it wasn't given. So this constant of proportionality is specific to the object or the type of medium that we're working with. So for this one, it's the meatball. Alrighty, so I had temperature final equals temperature of the surrounding object plus temperature of the object minus temperature of the surrounding, get that temperature differential, e to the kt. Filling in those things we know, the temperature final, it comes down to 200 degrees. Our temperature surrounding is 70 degrees plus temperature of the object was at 250 minus temperature of the surrounding is 70, e to the k, and it took 3 minutes for that to happen. I find one easy way to remember this is it is SOS on the right, and that just always kind of sticks with me. All right, to solve this, let's subtract 70 immediately. It is all algebra from here on out, so 130 equals 250 minus 170 is a 180, e to the 3k. Divide by the 180, that's going to give me 13/18 in a reduced format. Natural log both sides. Natural log of 13/18 equals 3k. And then I'd have 1/3. So 1/3 natural log 13/18 equals k. Now you definitely can put this in your calculator and get a decimal on it. I know I need a lot of accuracy, so that's why I just keep it as the expression, because then it's not rounded at all. All right, second part. Now we need to find out how long this takes, how long before it becomes 200, or no, not 240, becomes 140 degrees. So you can start with either amount. I think I'm going to go back to time 0 is 250 degrees, and at time I don't know, that's a question mark, not a 3. Question mark, we're down to 140, okay? And we do know our K value, right? So back to temperature final equals temperature of the surrounding plus temperature of the object minus temperature of the surrounding. That needs to be in parentheses, e to the kt. Oh, another thing, I don't put a negative k on there because it's going to turn out that this would be negative in the calculation. So if I put a negative in, okay, then this would have become a positive amount, but it'll take care of itself. The K will become K. If it needs to reduce in temperature, it's going to be a negative value. If it is going to grow and increase in temperature, it's going to be a positive K. All right, temperature final. We want to get down to, let's put it in a different color. We want to become 140 degrees. Our temperature surrounding was 70. The temperature of the object, I'm going back to the initial time when it was taken from the oven, so 250 minus 70, e to the kt, and I have that k value. I'll write it in next because I need a little more room, it looks like. Okay, I'm going to extend this page so that I can write a little bit bigger here. 140 minus 70 gives me a 70. So I have 70 equals 250 minus 70 is 180. E, this is my K value, so I'm going to have a 1/3 natural log 13/18 times some amount of time. Divide by the 180, that brings me to 7/18. I canceled my zeros. E to the 1/3 natural log 13/18 t. Keep solving natural log both sides to get rid of the e. We're at natural log 7/18 equals 1/3 natural log 13/18 t. Solve for t by division. That becomes a 3 times natural log 7/18 divided by natural log of 13/18. That's my t value. I'm getting that t turns out to be 8.707 minutes. So from the time it came out of the oven, I have 8.7 minutes until it's going to be at that 140-degree mark. Okay, good to know. All right, your homework is a Delta Math, and it is section 5.2. Good luck.